Awesome. A5. So A5, sorry, is essentially an opportunity for you to work on identifying and figuring out what the quantum numbers are for different orbitals, right, when they're drawn for you. And so there's there's a few different methods, right? The one that a lot of people love to jump straight to in Gen Chem is just simply memorizing what everything looks like, right? There's the whole thing where like s orbital is a ball and p orbitals look like dumbbells and d orbitals look like either four-leaf clovers or they look like a dumbbell with a donut in the middle and stuff. And then you get to f orbitals and higher, right? And then they start to have all kinds of like wacky lobe arrangements and stuff, and then it becomes a bit challenging to figuring out like, well, what is it actually in those cases. And so I'm going to go through and show you how to do it the proper way, I would say, in my mind, right, to do it right, because in that way you can apply it to no matter what the orbital is, especially when you get to part C, right, because there's some pretty crazy orbitals that I've thrown in there for you guys. But what we're going to be doing in to do it right is looking at it. So the first thing to do always when you're looking at an orbital and you're trying to identify what it is, especially if it's given the XYZ coordinate plane and stuff like that, is looking at two very important things. One, does it have any angular nodes? And an angular node is a node that essentially cuts through the XYZ planes, right? It's a plane essentially, right? It's for the most part a flat surface that like slices through, and then you have two different colored lobes, or in some cases, right, it's like listed as being plus or minus, and that has to do with the phasing of the wave function, right? Like we still have to remember, right, these are just simply mathematical depictions of the orbitals where we're looking at waves in these cases. And so, looking at, do we identify an angular node, right, which is essentially cutting through the XYZ coordinate axis. The next thing we're looking at is there a radial node, or are there radial nodes, right? And what radial nodes are basically invisible spheres that result in changes in the phases of lobes, right? They don't add lobes really to it, right? Like in essence, they just basically like cut in a circular, like a huge circle around it, around the orbitals, right? The lobes of the orbitals, to make more like hats. You could always say, right? Like I always refer to them kind of as like hats, because that's basically, right, you have your main one that's centered, toward the middle, and then you have hats that get stacked on top, right? You can add more and more hats and become more and more ridiculous. But that's the easiest way to think about it, right? So those are the two distinct things to always look for, is how many nodes you have, because the important thing is that if you know how many angular nodes you have, that tells you what the L value is of the orbital. And then if you know how many radial nodes you have, you can then add that to the number of angular nodes you have, and you can find out what your N value is, right? You can find out your principal quantum number in that case, right? And so that already gives you those two important parts, right? Telling you whether it's an s orbital, a p orbital, d orbital, f orbital, g orbital, h orbital, any of those things, right? You can figure those out from the angular nodes. And then by looking at how many radial nodes you have, right, you can figure out then, are you, at, the 1s, the 2s, the 3s, the 4s, so forth, blah, 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 right? You get all of those from there. Right. And those are always going to be, the most important parts really to figuring out more challenging things. The final thing to look at is the directionality, right? Where do the lobes lie, right? Are they directly along, one of the X, Y, and Z axes, right? Do they kind of reside in the middle? Do they kind of like balance themselves between axes in those cases? And in those instances, right, that then tells you which orbital you're looking at, right? Are you looking at the px? Are you looking at the py? Are you looking at the pz? Right? Are you looking at the 3dx squared minus y squared? Are you looking at the 3dxy? Are you looking at the 3, dyz? In those cases, right, you get that by looking at where the lobes lie, right, the directionality. And from there, you can then figure out essentially what the ML values are. And so one thing I realized on the answer key is that I must have made a mistake or something like that, where the plus minus is kind of missing on the ML values, right? Because you can't really distinguish them necessarily between two different counterparts very easily, because that always just simply refers to basically what your reference is. But in terms of narrowing it down to two of them, or even one, right? You can do that when it's completely in the z direction, because then it'll be ml is equal to 0 in that case. But you can kind of figure out where everything is. So with all of that said, let's go through it, right? So looking at this right here, right, we can see we just simply have a ball. It's centered in the middle. We don't have any lobes. There's no phase. There's no changes in colors, right? There's no phase changes that happen. And so that's telling us, two things. One, right, we're not looking at anything we're not seeing any radial nodes. We're not seeing any angular nodes in that case, right? So that already off the bat tells us, right, that L is equal to 0 in this case. And then it also tells us, right, that N is equal to 1. And so that tells us then, right, we're looking at the 1s orbital in this instance, right? And then in the case of ML, right, because L is equal to 0, the only ML value you can have is 0 in that instance, right? So that's what that tells us. Now for B, looking at B, one thing we can see here, right, is we have one angular node, right, along the XZ plane, right? So we have one that cuts that orbital in half and changes the phases in that case. So we have one angular node. Looking at it, right, we don't see any hats or anything like that being put on anything. And so that's telling us then that we don't have a radial node, right? So we have 0 radial nodes in this instance right here. And so in that case, right, that tells us then that L is equal to 1. And then because we have 0 radial nodes, right, the equation to figuring out then the N value, right, is N is equal to, the number of nodes is always going to be equal to N minus 1, right? That gives you the total number of nodes. And then the total number of nodes is just simply adding up the angular and the radial nodes. And so in this case right here, right, if we only have one node, then that means that N has to equal 2 in this case, right? Because 1 plus 1 is 2 in that instance, right? So that tells us then that we're looking at here is a 2p orbital. Now, the next thing to look at is that we can see that the lobe is along the y-axis, right? It's following, the orbital is following the y-axis. And so because it's following the y-axis, right, it's going to be the py orbital in this case. And so because, you have the py orbital, it has 0 z component to it. Because it has 0 z component to it, then that means that it's not going to be ml is equal to 0. And because then the only other two values you have are plus and minus 1, that means that this right here is then going to be plus or minus 1 in the case of the py. In the case of C, right, if we're looking at this right here, the first thing we can see, right, is that we have 4 different lobes. And so we can see that there's a phase change that goes, that involves an angular node along the YZ plane. And then we have another one that's along the XY plane in this case. And so there's 2 angular nodes. And now again, right, none of those lobes have hats on them, right? So that's telling us that there's no invisible sphere around it causing a change in phase, right? So there are 0 radial nodes that we can identify here. And so then that tells us again now, right, that L is equal to 2. And then N is going to be equal to 3 in this case, right? Because again, the total number of nodes is 2, so 2 plus 1 is equal to 3. And so that gives us then the fact that this is going to be a 3D orbital. Now, looking at the orbital, right, what we can see is that the lobes are sitting in the X and the Z directions, right? They're not sitting, right? They're not, pointing outwards in the Y direction. They're only pointing out in the X and the Z direction. So that then tells us that we're looking at 3D X Z orbital in this case, right? And so with that information then, the next thing that we want to figure out then is what the ML value is. And so now in the case of a d orbital, right, you can have essentially, 3 different sets of ML values, right? You can have 0, you can have plus or minus 1, or you can have plus and minus 2. So all of the ML equal to 0 orbitals, right? Those are all strictly along the the z axis in those cases, right? And so the 3dz squared orbital, that's the ml equals 0 for the d orbitals, right? Because it's along, it only has a z component in its name, so to say, right? It's only along the z-axis. When you look at it, right, I mean, it still has that like donut around it that goes along in the xy direction, right? But the primary component of it is in the z direction. The next ones, right, that you have are going to be then the the plus or minus 1. So those are going to have a little bit of z component to it, and that's going to be your 3dxz and your 3dyz orbitals, right? Because those have a z in the name still. And so you'll have those two. And that's what's happening right here, right? We have the 3dxz. So that tells us that's the plus or minus 1 in this case. Now, the last one, right, the plus or minus 2, right, that's the maximum, ML value that you can have. That's going to have 0 z component to it, and it's going to be strictly x component, x and y component to it, right? And so that's going to be your 3dx squared minus y squared and your 3dxy orbitals, right? Those are going to be your ML plus or minus 2 in those cases. And that same trend, right, that follows all the way through as you go along, right? It's the case for P, right? Your px and py are plus or minus 1, right? That's the maximum ML value you can have in that case, right? And the ML equals 0 is going to be your pz orbital. If you're going to the f orbitals, right, you have 4 different combos, right? You have the 0, plus or minus 1, plus or minus 2, plus or minus 3, right? The ML is equal to 0 is going to be your z cubed, right? Your and then you have like your z squared x and your z squared y, and then you have after that, right, it's like zx y, and then different things. I don't remember all the f1s off the top of my head, but you can kind of recognize them, right? Because you can kind of look at how much of a z component you have in your orbitals in those cases, right? And then at the end, right, there's like the whole like z or f x squared minus y and like y squared minus x or something like that. I remember. But those are all the different parts you have in those cases. So, the amount of z component, right, dictates, where within the range of ML value you are. So that's how I know, right, that this is going to be ML plus or minus 1. If we go to D, right, so now again, we're looking at it. We can see that we have one plane that cuts through, right? So this is an angular node right here. And so that's one angular node. We can see here, right, there's no hats. There's nothing sitting on top of there, right? There's no invisible sphere that's cutting everything. So that's 0 angular nodes. So again, now, right, this is L is equal to 1, and now N is equal to 2. So again, this is a 2p orbital. Looking at this now, right, we can see that it's the 2px. It's along the x direction in this case, the directionality of the orbital. And so then now, right, ML is going to be, again, plus or minus 1, right? So pretty similar to what we had for B in that case. For E, right, now this one looks very, very challenging. The biggest mistake people make in this case right here is they think that there's a radial node that's present, but there isn't. Right, so what we have is a one plane that's right here that includes the x and y directions, right, in the xy plane, right? We have one angular node that's right there. Now, the other thing that we have, right, is we have this weird cone shape thingy that's right here, right? That has like that circular shape to it. Now, a lot of people confuse that cone shape, right, that hourglass type shape with being a radial node. The thing is, it's an angular node, and it's actually 2 directions of angular nodes multiplied together to form that cone shape. In this case, right, it's not perfect planes, right? It's as if you took this plane and this plane, and then you did mathematical transformation, and they just got rotated 360 degrees, right? And that gives you like that cone shape right there. And the biggest tell as to why this is an angular node, not a radial node, is that it cuts through the origin, right? It cuts through the x equals 0, y equals 0, z equals 0 point on that coordinate axis. Radial nodes never ever go through the origin. They never ever go through the center. They're always outside of it. And they're always going to be spheres, right? They're always going to be a sphere. They're never going to be some kind of concave thing that goes inside of other orbitals, right? It's always going to be a sphere. And so it's always going to look like you're having like little hats on top of the lobes. It's never going to look that weird shape. And that's the biggest mistake people make when it comes to, in this case right here, right? This orbital or the 3D z squared orbital and so forth, right? Is they assume that that central one, because it has kind of curvature to it, and the way it gets, drawn and depicted is that it's, oh, this is a radial node, right? Because it's curved, it's not a flat plane. It's not true. It's actually two planes that are combined together mathematically, right, and rotated, and they give that weird shape. So in this case, right, because you have that weird cone shape, that's worth 2 angular nodes. You have that flat plane, that's worth 1 angular node. So this tells us, right, we have 3 angular nodes in this case. And then looking at it, right, we don't see any hats. We don't see anything that looks like an invisible sphere of nothingness, right? So that tells us then we have 0 radial nodes in this case. And so that then gives us the information, right, that we have L is equal to 3, right, because we have 3 angular nodes. And then 3 plus 1 gives us 4, right? And so then means that we're then looking at a 4F orbital in this instance, right? So we're looking at a 4F orbital. Now, which 4F orbital? Looking at this right here, we can see that this is essentially along the z-axis, right? This is, you have your dumbbell, right, that's following along the z-axis, right, and you have your 2 donuts that are kind of right there. And so, all of the donut things are always going to be in the z-axis, right? And so those are always going to be your maximum z values. And so that's going to, in this case right here, right, that's the fz cubed, right, z to the power of 3. And that means then that ml is going to be equal to 0 in this instance as well. Right? But that's how you approach these types of orbitals. And again, right, thinking about what's an angular node, what's a radial node is incredibly important, right? Because if you're seeing something that you may not be familiar with in terms of orbitals, right, being able to break it down and identify what's an angular node, what's a radial node, how many do I have of each one of them, will then at least give you the info of the n value, the l value, and then looking at the directionality is going to tell you essentially what the ml value, what the range of the ml value should be in those cases, right? And then you can try to deduce what the actual orbital name is. All right, so for A5F, looking at this right here, right, we have now, again, we have 4 different lobes, right? They're all different colors, and so we can see that we have one plane that kind of stays in the z direction, but it cuts in between the x and the y, and then we have another one that's similarly, but it's, 90 degrees rotated from it, right? It's perpendicular to it. And so you have 2 of those right there, right? So we have 2 angular nodes. And then we don't see any hats. We don't see anything looking like an invisible sphere of nothingness, right? So we have 0 radial nodes in this case. And so what that gives us then, right, is that L is equal to 2. And now N is going to be equal to 3, right? Because 2 plus 1 is equal to 3. And so that tells us, right, that we're looking at a 3D orbital. So now looking at it, what we can see is that the lobes of the orbital are sitting on the x and y axes, right? They're not in between them like we saw with the xy, or sorry, the xz orbital in C, right? We're seeing that they're directly on it. And so that's going to tell us that what we're looking at is the 3D x squared minus y squared orbital in this case. Right? And so the only other orbital, right, that it could potentially be would be the 3D xy. And so the reason that it's not the xy is that the xy would be then in between the 2 of them. And an easy way in my mind to kind of remember that, right, is that if you have the xy, right, if you have positive 1, right, in those cases, right, you're going to end up here. And if you have positive 1, negative 1, right, you're going to end up then in the middle, right? You're always going to end up in between them when you're multiplying them. In this case right here, we're subtracting them. And that's why they're going to, you can kind of think about them being on the axis in those cases. And so now, right, the final part, right, is the ML value, right? And so in this case right here, the ML value, looking at the name, right, looking at the orbital, there's nothing that's, there's 0 directionality into the Z axis. And so if there's no directionality into the Z axis, then that means that we're going to be looking at the highest ML values possible. And so in this case right here, right, that's going to be plus or minus 2. And so that's right, how you get these and stuff, right? So that's the approach that you should take anytime you're trying to figure out what type of orbital you're looking at, is breaking it down, looking at angular nodes and radial nodes and so forth.